The universe is vast, hundreds of billions of galaxies, trillions of stars, an unimaginable number of planets, and yet it's silent. The paradox began with a simple question, asked by physicist Enrico Fermi during a casual lunch with colleagues in 1950. Where is everybody? He wasn't joking. By all accounts, the math suggests the galaxy should be teeming with life. Our Milky Way alone contains 400 billion stars. With modern estimates, around half of those stars may have planets, and many are Earth-like. If life is common and intelligence arises even occasionally, then the galaxy should be buzzing with advanced civilizations. Some of them should have developed technology millions of years ahead of ours. Some might have colonized entire star systems. We should see signs of them, megastructures like Dyson spheres, radio signals, even probes visiting our solar system. But we don't. Despite decades of searching with SETI, the search for extraterrestrial intelligence, we've heard only silence, no confirmed signals, no evidence of extraterrestrial civilizations. The paradox is clear. The universe should be full of life, but where is it? In 1961, astronomer Frank Drake created an equation to estimate the number of detectable civilizations in our galaxy. The Drake equation looks like this: n equals r star times fp times ne times fl times fi times fc times l. R star, the rate of star formation in the galaxy; fp, the fraction of those stars with planets; ne, the number of planets per system that could support life; fl, the fraction of those planets where life actually emerges; Fi, the fraction where intelligent life develops; Fce, the fraction that developed technology capable of communication; and L, the length of time such civilizations release detectable signals. At first glance, this equation suggests there could be hundreds or thousands of civilizations out there. But the truth is, we don't know most of these numbers. We can measure R star and FPE. We know stars and planets are common. But what about FL? How often does life arise? We have a sample size of one, Earth. For all we know, life could be incredibly rare or incredibly common. And Fi, the fraction that develops intelligence, is even more uncertain. Dinosaurs ruled Earth for 165 million years and never built radios. Intelligence might be a fluke. Then there's L. How long civilizations last? Do they survive for millions of years? Or do they destroy themselves quickly? This is where the great filter enters the conversation. The great filter is an idea introduced by economist Robin Hanson in the late 1990s. The concept is simple but profound. Somewhere along the path from simple matter to galaxy-spanning civilizations, there's a nearly impossible step. A filter that almost no species passes. This filter could occur at any stage. Life might be incredibly hard to start. Complex cells, eukaryotes, may be nearly impossible to evolve. Intelligence might be rare, or civilizations might always destroy themselves before colonizing space. If the great filter is behind us, we are lucky. It means we've already passed the hardest part. Maybe life itself is vanishingly rare. But if the great filter is ahead of us, then it means advanced civilizations tend to self-destruct. Nuclear war, climate collapse, rogue AI, or something even worse. The silence of the universe might be the whisper of countless civilizations that failed. One optimistic possibility is that the great filter is already behind us. Maybe the emergence of life is so rare that almost no planets achieve it. Earth might be a miracle. But there's another, far more unsettling possibility. What if the great filter is ahead of us? What if the reason we don't see aliens is because all advanced civilizations self-destruct before they can colonize the stars? Think about our own species. We've been a technological civilization for barely 100 years, yet we already face existential risks, nuclear war, Enough to end civilization overnight. Climate collapse, destabilizing the very planet we depend on. Artificial intelligence, which could spiral beyond our control. Pandemics, natural or engineered. Asteroid impacts or gamma ray bursts. Maybe every intelligent species invents technology, but also invents its own destruction. Or perhaps the universe is full of predatory dangers. Maybe advanced life attracts attention, and something else out there wipes them out. The silence might not be emptiness, it might be a warning. There's another explanation: rare earth. The rare earth hypothesis argues that while simple life may be common, complex life, like animals or humans, is incredibly rare. Earth had a perfect set of conditions: a stable star not too big or small, a protective magnetic field and thick atmosphere, a large moon to stabilize its tilt and seasons, plate tectonics to recycle carbon and maintain a stable climate, a location in the galaxy far from deadly radiation. All of these factors may be rare. Perhaps we are not just alone in the galaxy, but in the entire observable universe. It's a humbling thought. The silence might not mean danger. It might mean we are special. If we are alone, the responsibility is enormous. We are the only known species capable of shaping the future of life and intelligence. This means we must survive. We must overcome our short-term instincts, avoid self-destruction, and spread to other worlds. Because if the great filter is ahead, our time is limited. And if it's behind us, we might be the only voice in the dark. The great filter is a mystery we may never solve. But one thing is certain: our place in the universe is fragile and precious. Maybe the reason we don't hear others is because we're meant to be the first. If this journey into the Fermi paradox and the great filter sparked your imagination like this video, subscribe and join us every week here at Skyward Space Quest as we explore the biggest questions in the cosmos. Until next time, keep looking up.